Okay, so this is the ripple tank. It's basically a shallow trough of water, and we have a beam here, and you can either tap the beam and send a ripple across the surface of the water, and the ripple is actually going to be a big flat line. It's called a plane wave, moving across the surface. And then we can explore what happens to those ripples. So I could, for instance, put an obstacle in the way of the ripple and see what happens to the ripple. You see it actually reflects off that. And put another object in the way and send a ripple towards it. I can make a narrow gap so I can explore things like diffraction. So with these two placed in the liquid like this, and then I can have this vibrating and sending several plane waves out across the surface and see what happens when they meet this gap. I can also try making the liquid shallower. I could do that by tilting this up, or I could do it by placing a piece of glass in the liquid, and then I will have above this piece of glass here, it will be shallower, and we can see what effect that has on the wave as well. Okay, so now the other thing I'd like to show is that what happens when this does actually switch on and we have it rotating. So modifying the resistance, and here we have some plane waves travelling out. And if you actually have a good look at the surface of the liquid, it's possible to see, if you get it just right, I think we can just about see the ripples on the surface here. You can hear. The light has to be just perfect. And because the light has to be just perfect, we use a projector, which, if I can just find the switch. So now I've switched on the projector, and it actually projects onto the board, and if we switch off the lights, which is what we'll do in a second, we can see nicely some plane waves. Okay, so here is an incoming plane wave, and this is showing the direction of travel or energy propagation of that wave. So let's step forward frame by frame. Okay, and it's about to strike the surface, the point we were looking at anyway, the tip of this point. As it strikes the surface, it's reflected. And we can see that this angle here is approximately equal to this angle here. And that's the law of reflection. The angle of incidence is equal to the angle of reflection. Okay, so now by placing an obstacle in the path of these plane waves, we should be able to see some reflection. I think that's pretty clear. Okay. You can also see what happens as the waves pass an edge. Small amount of diffraction coming around the edge here. It will come out better in slow motion. Okay, now we go for full-on diffraction. So this is where the gap size is relatively close to the wavelength of the incoming waves. So if we increase the gap size, you can see the effect it has on the amount of diffraction. So I'm decreasing it towards the optimal, which is when the gap size is equal to the wave length. And I'm going smaller than that, and we see that eventually the diffraction breaks down. Okay, so that's diffraction and reflection we've seen. Okay, so I've gone ahead and analysed this frame by frame as well, The red arrow, as before, represents the direction of the wavefronts moving. The black line here is where I approximate the wave to be at this moment in time. And I'm going to step through it frame by frame. So you can see the wavefront has moved forward a little bit. And I should explain at this point as well that this actually is the shallow water and this is the deeper water. So at the boundary between medium 1 and medium 2, we're looking to see if there's any effect. Okay, so we see the wave move forward. We're beginning to see a small effect. Again, it's hard to notice, but there is an effect there. Okay, the point we're looking at now strikes the boundary. Now, it is difficult to see in these early pictures, but as you move forward, I think it's clear to see that the wave has definitely changed direction. And by the last picture, it's pretty clear the wave is moving in a different, it's been twisted a little bit or changed direction. So this event is actually called refraction. And we can analyse it the same way we analysed reflection. We draw on a normal line perpendicular to the boundary between the two materials. And then we can measure the angle of incidence, measure the angle of refraction this time, and this time we find that the angle of incidence is not equal to the angle of refraction. So we can explain this actually in terms of wave speed and what's happened to the wave speed. So let's go through this again, this time concentrating on wave speed. So I'm going to try and work out how long it takes for the wave to move from this line to this line. So in the first step, in this part, in medium 1, we'll be able to work out how long it took and work out the speed. And in medium 2, which is here, we'll be able to work out the speed as well. Okay, so that is when we reached the finish line. So the wave moving in medium 1, the deeper water, reached the finish line here. The wave moving in medium 2 isn't at the finish line yet. So if you think about this distance travelled here, and this distance travelled here, the distances travelled will be directly proportional to the speeds. So for all intents and purposes, or the velocities, for all intents and purposes, we can just take these distances as speeds. Now, the program I'm using, I was able to measure the length of these arrows, and they came out as 8.1 and 5.7. I'm sure if you pause the video, you can get your ruler out and check. They'll be the same ratio anyway, even if the aspect ratio of the video changes. Anyway, now we look at the angle change from 34 to 23. There's been a change. So, it was discovered that the ratio of the velocity of the wave in medium 1 compared to the velocity in medium 2 is equal to the ratio of the sine of the incident angle to the sine of the refracted angle. Okay, so we should check this. Okay, so we'll test it out. If you type in 8.1 divided by 5.7 on your calculator, you get the result 1.42. And if you take the sine of 34, the angle of incidence, and the sine of the angle of refraction, 23, you get 1.43 for this particular example, which is pretty much the same. I mean, given the experimental error in this, and I've actually done this with the real results, and I haven't modified them at all, it's remarkable how accurately it matches up with this theory. Okay, so this is more commonly known as Snell's law. It was first accurately described by Ibn Sahl of Baghdad, and but it is better known by Mr. Snellius. Right, so the important things about the formula are that as long as the units for speed, velocity, are the same, centimeters per second, meters per second, kilometers per second, it doesn't matter, it's a ratio. This symbol mu is what's called the refractive index, and because these are both ratios, this doesn't have any units either. And this law applies to anywhere where waves go from one medium to another. For instance, sound waves moving from water to air. There would be a boundary where the speed is different at the surface of the water, and you could apply this rule to it. And you could go ahead and calculate the refractive index and write them down in engineering books and use it for all kinds of useful calculations. Okay, so thank you for watching, and a special thanks goes to Mr. John MacArthur for some of his kind suggestions and advice. And guys, subscribe, like, share. And if you hang around for a second, you get a taster of my next video.